Word. All right, so appropriately got a substitute teacher for, I can't do the voice as well as some of you could. I also called in Dr. Sherpa called in substitute teacher because you guys were not taking her seriously enough about your class presentations, which were supposed to be today. So she wrote on the board, 4 of you have responded to my email with topics. There's 15 of you. So I should be getting topics. In fact, Major, I think you're going to get demoted. You're not up there. You haven't given, several of you haven't given me a topic. So I'm moving, or she's moving the class presentations to, we're going to just do them next Thursday. And so Tuesday, I'll ask you, if you haven't, I'll be bugging you in class on camera, what your presentation is, and I'll pick what times we're doing them. So one will probably be late afternoon. I have presentations that morning too. So the first one will be later in the afternoon. And the other thing is nothing is due this weekend. So your teacher is being, my mask is crooked and here we go. Yeah, if you have late labs, let's just get them in. Let's get all the late stuff in. And so next week we can focus on your presentation. You can send me an email whenever you want with what your topic idea is. And then there was a question. Jeremy actually sent me an email today about his topic. And I wanted to clarify that the description for the last presentations for the molecules, you had to have 2 scientific studies. This one is innovations. And so everything you find is going to be based on scientific studies, right? Because somebody had to create this and do experiments to see if they could get it to work. What I want you to really talk about is the pros and the cons of the innovation, because money's going to be the biggest con, because whenever something's new. But there's some really cool topics that these 4 people have had some really interesting topics. But if you gave me a topic, it was Jeremy who was concerned. That's why you, and it's going to be a beautiful weekend. So that's also why I moved it to Thursday. So you can all enjoy your weekend, get any late stuff in, just do it tonight while it's still rainy. And then enjoy your weekend. And then next week we'll be moving on. So with that, so our last topic is nuclear chemistry. All right, so what is it? Let's see if we can get more participation since the captain is here. Well, it is the study of the nucleus. Glad you asked. Really pondering if all of their outfits are made out of this kind of material, because they're extremely hot. They should have made them out of spider webs. Spider-Man, DC Comics had it better off. Was Spider-Man DC, or is he, well, he's Marvel? Okay. I don't know my comic strips. Oh, so that's the other comment about class presentations. So you can also do one of the innovations some of you wrote about, something to do with state of matter. So cleaning up the mess. You can pick something that you didn't write about, just with my approval. You can also do something. So your last lab, I will put it up there. It's not going to be due until the end of next week. You're going to get to write on something about nuclear, which is about the nucleus. The nucleus has a lot of subatomic particles. We're going to talk about 2. We're going to talk about the nucleons. So what are the nucleons? Anybody remember?
Protons and neutrons.
Protons and neutrons. You guys remember those? They are also known as the massive subatomic. Both of them. They account for virtually all the mass. But if you would like to, there's new subatomic particles being found. There's stuff on dark matter. There's some really cool stuff that deals with the atom and the nucleus. So if you'd rather look into something like that for your innovation, that is a wonderful topic. All right, so Damon got one for the team. How about isotopes? Anybody remember the definition.
Are they the same element but a different mass or something?
Yes. Same element, but different mass. I'm trying to decide if Major should get up on the board. Is Major higher than a captain? Is he like my, oh, wow. All right, thank you, Major. Different mass. So in terms of subatomic particles, how would that work?
Same protons, different
Same
neutrons.
protons, different neutrons. All right, that's important. That's the key to what we're going to be doing. The history is extremely fascinating, and we'll see small glimpses of it throughout this. There's some fun pictures of some really famous people. Some people helped me to be, right, this buff instead of that little skinny kid. All right, these guys are called nuclear chemistry. Does anybody know who coined the term radioactivity? Let's see if anybody can come up with it. Usually, last term Major used, sorry, the mask is hurting my nose. Kids apparently have different shaped noses. And anyway, radioactivity, it was Marie Curie who coined the term, and because they knew there was something that was going on in that huge piece of uranium that had activity of different than what they had seen before. What we're going to talk about, nuclear chemistry, is we're going to look at these three particles, so alpha, beta, and gamma. And they are a type of ionizing radiation. So other types of ionizing radiation is radiation that knocks electrons out of orbitals. That's what it is. So UV light would be one type, but that's not here. These are specifically from the nucleus. So these are particles that are ejected from the nucleus. An unstable nucleus. And that is what nuclear chemistry is. So if you don't have your periodic table, tonight is extremely periodic table dense because we're going to be using this a lot. So make sure you have it handy. All atoms have an unstable nucleus. Not every isotope, but every element has isotopes that are unstable. It has to do with the ratio of protons to neutrons, and we'll get to that on one of the later pages. And so if the ratio is not perfect, in that nice band of stability, and that's what they call it, those scientists, then it's going to eject one of these. There's actually other ones too, but these were the first ones. And anybody know who won a Nobel Prize for these first two? I mentioned it last term, but nobody would remember that. So Ernest Rutherford, anybody remember him?
He did the gold experiment.
He did the gold experiment. Christian, what did he find from that?
I kind of forgot, but like, didn't he like something where like he shot something through the
Keep
thing?
going.
He saw.
And how much went through?
Like not a lot, right? Or was it
99.9999999999999%? You all remember that now that I usually cover the whole board or the whole piece of paper. So he shot gold particles. I'm sorry, he shot alpha particles at a piece of gold, and they thought they were going to deflect, and they didn't. So he did not win the Nobel Prize for that experiment. He won the Nobel Prize many years before that experiment for finding these particles and figuring out what they were. So the symbol for alpha and beta, these are the Greek symbols. So alpha looks like a fish, beta looks like a butterfly with half its wings are gone because it had a mutation probably, and gamma is the dead fish. It's dead. Gamma is not a good thing. None of these are good. And symbols always have numbers with them. So you guys remember doing this where we put way back It's like the very first lesson, the Chem 221. So back in January, feels like a different lifetime. So I'll go through what the numbers mean in a moment, but let's put the numbers there. So we'll put a 4 and a 2 for the alpha before the symbol. For beta, we put a 0 and a -1, and for gamma, a 0 and a 0. So those are the symbols. There is another symbol for each one of them. We're going to go with the symbols I just drew, but does anybody have an idea what the other symbol might be for this one and why? What does the 2 mean? The lower, that 2 that's underneath.
Isn't it mass?
No, it is, the lower number is the atomic number or the number of protons. So if you look at that handy dandy periodic table, this is helium that we're talking about. And so some people will actually write the symbol as He, but it is not helium. And that's why we're not going to write it like that, because this is the nucleus. And so what this is it's 2 protons and 2 neutrons in one package. So you'll see it often diagrammed like those would be the protons and these would be the neutrons. It's one package. The upper number is the mass. So the top number is the mass, or the mass number, which is the protons plus the neutrons. So it's telling us it's 2 protons and 2 neutrons. It is the nucleus of helium. There's no electron. So an unstable nucleus that's just too big, like all these bad boys down here, they're just too big. This is a fast weight loss. They just, it'd be like you just boom, in one moment you lost 4 nucleons in one packet. This is massive. On the nuclear scale, this thing is like a T-Rex, and it is going to knock everything out of it. As far as ionizing radiation, this is extremely dangerous because of the mass. This guy is huge. So what blocks it? Actually, a piece of paper or your skin. Why, if it's a T-Rex, so that T-Rex comes into your bedroom right now and is going through it, and all you do is hold up your hand and it can't do anything. Why would your hand, the skin on your hand, block it? Or this piece of paper for the periodic table?
Too big to fit
It's too
between.
big. The problem is, if it gets inside of you, like you breathe it in, and so then it's inside of you, it's now trapped inside of you because it can't get out. So it's like the T-Rex is locked in the room and it's gonna just destroy the whole room, right, that it's locked in. All right. The beta particle, the other symbol for a beta particle is E. It is an electron from the nucleus, ejected from the nucleus. It has incredibly high momentum. So all electrons are right moving, their vibrations. This guy is being ejected from where all the mass is, and it's just chaos moving. So this would be like if we took Major and we wound him up. We just gave him so much caffeine, like just kept making him drink it, and he's just bouncing off the walls, and there's nothing stopping him. Eventually he slows down as the caffeine wears off, and he becomes just like the rest of us, what we see here, very calm and serene. But this guy is going to cause damage. It's going to knock other electrons out. So you've all been there. I mean, we could use Tristan as an example too. When what are those parties called when you go to the and everybody's dancing like that and you're just banging into each other, right? And so that's the idea of a beta particle. So it's not like a regular electron because of where it came from. And I never give myself enough space when all I have is a little box because I'm used to having the whole everything to write on. All right, the electron, I keep pausing because I'm waiting for the question. What's in the nucleus? Protons and neutrons. And the electrons are orbiting outside. Well, they're pulses on the outside. So how the heck did this electron end up in the nucleus? And it didn't get trapped in there because it can't get there from outside. Those pulses can never make it to the nucleus. It's not possible in quantum mechanics. So what this is a neutron decays. And that's what a beta particle is. So a neutron has a mass of 1, but it is not a proton. So that's the symbol of a neutron. Mass 1 on top, 0 down below. I wanted to make a quick comment about the symbols. So when I taught it to you, we showed the mass number, the protons and neutrons up above. The atomic number was the protons. Another way of thinking of the atomic number is it's the charge. Since we were always counting protons, it was always a positive charge, so a +2 or whatever. But working with nuclear chemistry, some people think of it that way, and it makes more sense for them. And so this gets a -1 because electrons have a -1 charge. A neutron has a 0 because it's not a proton, it has no charge. And what happens is the neutron decays into a proton and an electron. So that's a proton. I'm sorry. And we should write this as a beta particle. I don't like showing it as an electron because, again, it's not the same as a regular electron. It's got an outrageous amount of potential and it's going to cause damage. A regular electron is not going to cause damage. It's not ionizing radiation. You can show it either way, but at least respect that. And you'll see it both ways in the literature. So a proton plus an electron or a beta particle. Now, nuclear chemistry, and we'll see this on the next page, balanced equations are done differently. So we're not balancing so the elements are balanced. That's a chemical equation. Nuclear chemistry, the numbers on top have to be equal on each side of the arrow. So we have a mass of 1, and over here we still have a 1. And our number in the lower number has to be the same. So we started with an atomic number of 0, and here we have a 1 and a -1, and that's 0. And you'll see that on the next page. And that's really the big point of today's lecture, is how to write these equations and these 3 types of particles and a couple other ones that we're going to add later down here. All right. Gamma, it has no mass. So actually, let's back up to the beta particle. It does have a mass. The mass is actually 1/1820th of an AMU. An AMU is an atomic mass unit. This has a mass of 4 AMUs. That is massive on the atomic scale. If you go to the last page of your notes, sorry, it's not there. An atomic mass unit is about 10 to -21 grams. So on our scale, it's like, well, that's nothing. But on the atomic scale, this gets a 4, and this is 1/1820th. So this is 7,000 times bigger. So this is like a mouse, and that's like the T-Rex. But again, this is like major on caffeine, though, a lot of caffeine. And so he's going to cause damage. T-Rex is going to cause more. T-Rex would probably take major out if they were in the same room. But if he's on all that caffeine, T-Rex might never come close to him. So, all right, this, though, truly has no mass and no charge. It is just high frequency. Remember frequency from last term? High frequency electromagnetic waves. It is just waves. It is higher than UV. And we all know that UV light can cause damage because it can cause skin cancer. It can also do wonderful things for us. So gamma rays, so because they're really high frequency. So back to what can protect. So gamma, that's my dear friend Bruce Banner got exposed to too much gamma. And you guys saw what happened to Bruce. So your teacher, she actually worked with gamma radiation when I was at Penn State in my undergrad years. And so it was, the only thing that's going to block it is lead, PB, or denser. So what they usually use is concrete, like several feet thickness of concrete. And so you would, all the labs at universities are connected. There's underground tunnels that connect the labs in the old days. I don't know how it is now because there's so many more buildings, but all the labs at Penn State, there were these underground tunnels that connect them. And as you got higher into your science years at Penn State, you learned about the tunnels. But the gamma radiation thing was deep under one of these tunnels. And so it had to be underground, and then it had like huge walls of concrete, and you would put your sample. So I was working with bacteria and seeing the effects of gamma radiation on mutation rates and stuff. And so you'd take your sample of bacteria and you'd put it in this little thing and you'd push a button and it would take it in through the concrete. And then I would sit there for 20 minutes while it zapped it. And then it would come back out. And there was a candy machine there. That's all I remember. I think it's the bizarrest thing that they put a candy machine there. I think it's really bizarre that they have a candy machine next to what should be our classroom right now. And so but the candy machine was broken. And so I'm sure everybody who had to go down there, you were bored because you had to stand there for 20 minutes, would get something from the machine, and it always ate your money. And so everybody would beat the machine, which is why it was broken. But anyway, beta is, so alpha is the easiest to block. So down here, which is the greatest degree of penetration, would definitely be gamma. And that's why you have to have, oh, that was the other thing here. It's higher than UV, and it's also higher than X-rays. So gamma is greater potential than X-rays, but you have the idea of X-rays. So in the old days, when you went to the dentist and they were going to take X-rays, you had to wear the apron to protect yourself. But now we've made X-rays and everything very pinpoint specific, so they don't do that. But beta, what's going to block that is really thick plastic. Lead is going to block all of them. The only thing I know that's higher than gamma is cosmic rays. And so cosmic rays have a mix of gamma in them, but that's why when the astronauts go to the moon, their shields actually are lined with gold because that's even denser than lead. And I don't know how that all works. The thing that's really nice about thick plastic, I don't know, it's about that thick. You can see through plastic. Like every one of you can see through plastic. Only some of us can see through lead or gold or concrete. And so if that's your superpower, don't tell me about it. Or we can talk after, right? So thick plastic was nice. So I worked with a lot of stuff in my graduate school that was either alpha or beta. And so we'd work, the plastic shield was there. Anyway, the question that's really important is this: which type has the greatest ionizing potential? And that is, anybody know? Got it, 1 out of 3 choice. Which one ionizing potential is most damaging? Maybe that's what I needed to clarify what that means. So which one has the greatest potential to cause damage?
Beta particles?
No.
1 out of 3.
So he's eliminated beta. Anybody want to take another guess?
Gamma.
They all cause damage. Let's go back there. They all have the potential to cause a lot of damage. It's not gamma. Anybody want to go for 3 out of 0? 0 out of 3? It is alpha. So knowing it's alpha that can cause the most damage. Remember, alpha is the T-Rex. This is just major on a lot of caffeine, or Tristan, you at whatever one of those, whatever, I can't remember what they're called.
Are you talking
gamma.
about a mosh pit?
There you go. Thank you.
Okay.
I don't know what the name is. I told you, your teacher's not the most hip. And alpha because of the size. On the atomic scale, there's no comparison. This is the T-Rex versus major, or any of you on caffeine or in the mosh pit or whatever it's called. So gamma, even though it has the greatest potential to penetrate because it's just waves, it's going to go right through you. So the chance of it causing damage is actually pretty close to zero. It's just if you're in like a blast of a nuclear bomb, there's going to be so much gamma going at you that something's going to happen. Yeah. All right. Whereas alpha, the good news is we can block it. It's just when it ends up inside of us, which is, so should you be worried? Your best defense is to walk away, actually run. So run away. This is when you take physics, there is something really cool that happens, and I don't know why this happens, but there is something called the inverse square effect. And most things in nature have this effect that for every, there's like all these relationships. It happens with charges also. So there's an inverse square effect. So for every, like the distance you get away, it would be your exposure becomes, so this would be, so if you move 2 feet away, you're at 1/4 of the exposure. If you move 10 feet away, you'd be at 1/100th the exposure, something like that. So the further you are, the amount of exposure goes down exponentially by this inverse square relationship. And yeah, and so you want to get away. That's when the whole thing happened in Japan. That's why that was, and then actually even worse was Chernobyl, because they didn't have the people evacuate immediately. They're like, oh, nothing to worry about. Chernobyl is actually really interesting right now. That would be an interesting topic. One of the reactors of Chernobyl came back on, is actually doing a nuclear reaction. Water somehow seeped into it, and that can start the nuclear reaction. And so even more interesting, and Kobe, this might be a fun topic for you, is Chernobyl, which was the big, gosh, it had to be 40 years ago. I think it was 82 or 86 was Chernobyl. So sometime in the 80s, so it was in Russia. It was before the Soviet Union, I think, collapsed in 87. So it was still the Soviet Union. And they had a nuclear, an issue happened at a nuclear power plant, and it released a whole bunch of nuclear radiation, and the people in the area got exposed, and they didn't tell anyone. Over the next 4 days, these alpha, beta, gamma particles and the other particles were released into the atmosphere, and they were being picked up by in Europe. They were detecting small levels, and they knew it had to be, and they could pinpoint exactly where it happened. And Soviet Union kept saying, nope, 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 nope. And then they finally said, okay, yeah, you got us. Every cow died in the area, like when they went over and could see this is, and most of the people, I've had several students who actually grew up there at that time, and they end up like people who grew up near Hanford, used to call it the Hanford necklace, which is they have thyroid cancer, so they've had their thyroid removed. Most of the women ended up with reproductive types of cancer and stuff. I had a student, this is like 20 years ago, and she was from there. And she'd said there was no female in her family that was still alive. And so she would have just been a small girl. I think she had thyroid cancer. But anyway, what I was getting at for you, Kobe, they were until recently, when this reactor has become active again. It's a national park because there are rock formations that do not exist anywhere else on this planet that happen because of the nuclear accident that happened at Chernobyl. And there is plant life that doesn't exist anywhere else. And so there's actually some really cool stuff that has happened, and they're studying it to try to understand some of that. But anyway, that would be a really cool topic if somebody wants to look into that. Should you be worried? There are bigger things to worry about, like, you know, we're all worried about coronavirus, but we should be more worried that the epidemic, there is a pandemic that was going on before that, which is the rate of diabetes. So the World Bank actually proposed 5 years ago to put a tax on soda, or else we were going to be bankrupt from the issues to healthcare. Coronavirus kind of has covered that up, and then everybody ate crappier for the past year. So like fast food just is like skyrocketed the amount of profit they made, and people are eating even crappier, and they're like, hey, I got vaccinated, I can eat crappy food. It doesn't quite work that way. Eat healthy. All right, sorry, I went on a rant there. We should put the mask back on. So there are other particles. Oh, back to the thing with these first two particles. So Rutherford found these. He got a Nobel Prize in chemistry. He made a comment when he got the Nobel Prize, and so they never gave him the second prize that he very much deserved for coming up with the idea of the nucleus, which of course, again, is always just an idea, but it does explain quantum mechanics in an elegant way. Positron is the antimatter of an electron, of a beta particle. So it is often shown as a 0 and a +1 beta. I show the plus to emphasize it's a positive. So it has a +1 charge and a mass 1/1820th of an AMU. So we show it as 0. So it's an electron with a positive charge. It comes from proton decay. And so what happens here, look at this, I have lots more room, is a proton decays into a neutron plus a positron. So this is the proton, mass of 1, charge of 1, becomes a neutron. The neutron stays in the nucleus. So this stays in the nucleus. Same like up here, the proton stays in the nucleus. It just, right? We just changed a proton into a neutron, but when you do that, you have to account that there's a difference in the charge, and that's the positron, and that will be given off and cause havoc, just like the electron did up here, the beta particle. It can also be shown as a 0 + 1 as an E, because it's the counterpart to it. A neutron, we already talked about that, is a 1, 0, little n. They're always shown as little small letters because they're subatomic particles, and a proton is a 1, 1p. Obviously could not be phosphorus because phosphorus would have a 15 there. So this is a proton. The picture here is the radium girls. So radium is radioactive. Anything after bismuth has an unstable nuclei. But a lot of them, they're around for 1 billion years. Their half-lives are 1,000,000 billion years. And so it takes that long for half of them to decay to give off these particles. But radium does. And so this is, gosh, like 80, maybe 100 years ago, radium glows. And they didn't know why yet. And so they painted watches. So now, of course, we have LEDs and other ways to make our watches glow. But so they painted it with radium. And so you would have a watch that would glow and you could see what the numbers were. And so to paint the numbers on a watch, long before digital watches, you need a very precisely pointed paintbrush. And so the woman would lick the paintbrush and paint it with the radium, and they kept licking the paintbrush, so they got exposed to their mouth a huge amount of radium, which is an alpha emitter. And so in their mouth now is a huge amount of alpha, and so a percentage of these girls ended up getting tongue cancer, throat cancer, mouth cancers, and die. And so there's actually a Broadway play called The Radium Girls. There was a book and stuff, and I think it was made into a movie. I have not seen the movie, but that's what that's about. I don't remember if anybody did radium as their topic last term, but anyway, there's lots of fascinating history of stuff as we learn, and lots of fun cartoons also. All right, so we're going to go through the types of decay because that's one of the big points here. And you can make a prediction of what type of decay something will go through, but it will only be a prediction. You can only know if you actually do the experiment. And once they know, it's always that kind of decay. So uranium-234 goes through alpha decay. So you will be told what kind of decay it goes through, or you'll be given in blanks and you'll figure it out from the blank. And so that's what we're going to go through here. So once I show you these first two, I'll give you a chance to try these. So the way we write this, I just remember writing symbols. The 234 is the mass number. And yeah, we can show it, it's read as uranium-234. So when we type it out, I usually write it like that. But when we write the symbol, we show the 234 up here. And then the lower symbol for uranium, of course, will be on your periodic table. And that's the 92. We're not going to be using the masses because we're not doing any calculations with mass here. So we just need the atomic number. So that's on the periodic table. And the mass number, again, will be given to you. All right, it is decay, so there is an arrow. And we get the particles, so alpha with a 4-2 plus, now we have to figure out what it becomes. The arrow is like an equal sign. Some people write an equal sign. I don't really care. You're going to see me write an arrow. The top number has to be the same on both sides. The mass has to be equal. So if this is 4, this has to be 230. That tells us absolutely nothing. And then this has to be a 90, because 90 plus 2 would give us the 92 protons. And then element 90 is, oh, look at that, my good friend Thor. So it is named for thorium, for Thor. And that's it. That's our equation. This is called the parent nuclide, and this is called the daughter. It's actually called the mother and daughter because women are unstable. So you will sometimes see that where it will say what's the daughter nuclide, or what nuclide is given off, and it would be thorium. Or this is what it became thorium, and the alpha particle is given off in that. All right, to do beta decay, so another isotope of uranium-235. So it's still number 92, because again, isotope, same atomic number, different mass. And this one goes through beta decay. So beta means we give off. By the way, it's a question often asked. It doesn't matter if you show the alpha particle first or last. You do want this plus sign there, though, to separate the two. And right, there's our beta particle. The mass does not change. The only thing that's going to change your mass is our alpha decay. What is my new atomic number?
And 93.
It is 93. So, because -1, 93 gets us back to 92. So when something goes through alpha decay, it actually becomes smaller on the periodic table because it's losing protons and neutrons. But beta decay, if you remember, that is a neutron becoming a proton. So it always moves to the next element up. And so we get Neptunium. So these are named for the planets. Uranium was found first, and then they found Uranus. They named it after it. And then the next two elements, when they discovered them, were named after the planets as they were discovered. So uranium, if you don't know your planets, Neptune is the next one out, and then Pluto, which is again considered a planet, I think this week. Next week it might be something different. So you can try these. The one thing, and I'm going to take a break, or you can take a couple moment break. Electron capture means you're going to capture it. So that would mean the electron is a reactant. So they started making the colliders and they would see, hey, what happens? And then these just fill in your lower numbers and see what you get in the blank. So I'm going to pause. Okay. All right, let's go ahead and go through these. Hopefully you're back. And so I-131, your handy dandy periodic table. We need the upper number for iodine. So again, remember, on the periodic table, most periodic tables show the atomic numbers above, but in this we write the mass above and the atomic number below. That's just how it's done. I didn't make up the rules. And again, you will be told the type of decay. And beta, no change in the mass. Atomic number moves up by 1, so it becomes number 54, and that is xenon. Polonium 210. So based on the size of the mass is how you're going to find it. So 210 is down here. So polonium is one that was named by Marie Curie after her home country that did not exist when she named it, because this is when World War II, everything was being taken over by Germany. So polonium is number 84, and it goes through alpha decay. So something I also wanted to mention, if you look on most periodic tables, once you get down here to polonium, they're all in parentheses, and that's because they're man-made. And these are the only isotope, or the isotope that they made. A lot of them, they've made other isotopes. Yeah. All right. Oh, they did name 106 after Seaborg. That was appropriate. All right. So the new mass, we lose an alpha particle. So the mass decreases by 4, and the atomic number decreases by 2. So that should be lead. So alpha decay, you always drop 2 down. Alpha decay is a huge change in mass. And as they get smaller, they're usually more stable too. Lead is stable. It does have an unstable isotopes. I don't remember what the unstable ones are. You don't need to worry about it. If it tells you something goes through alpha decay, you do that. What this picture is showing is that most things make something that is also unstable. So this is probably uranium-238. It goes through an alpha decay, then a beta-beta, then another alpha, then another alpha, 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 beta, beta, beta. And so it keeps going until it gets to something that's stable. And then it stops. This whole thing, though, takes billions of years because each thing has a different half-life. Calcium 41. All right, back to something else. Is alpha and beta and gamma are called natural decay. And that is because this is just what they do in nature. If it's an alpha, if uranium-234, naturally will be off an alpha particle. The electron capture, this is man-made. So this is probably was done like at the Lawrencium lab that I was talking about. So they put an electron. So here you do show it. If you show it as a beta, that's fine too. But we took a calcium and an electron, and they wind them up going super fast with magnets. And so here you have 2 reactants. So again, decay, only 1 reactant, and it's not called a decomposition. A decomposition is a compound falling apart. This is decay of the nucleus. All right, mass doesn't change, and the atomic number would decrease by 1 because you have the -1 is on that side. And the key word is that word capture. Historically, the term was bombarded. So it means you're hitting it really hard. So you guys all played dodgeball? When I was a kid, so I grew up during the Cold War, right? In the 70s, we played bombardment. And so I don't play dodgeball. Everybody I work with, because most of them are younger than me, they play dodgeball and they think, oh, it's a fun game. And I was also a kid with glasses. So some of you wear glasses may have not liked dodgeball either because your glasses always got broken. Plus, I was a little girl, and so the boys would always throw it as, I mean, it's a terrible sport. And bombardment was like no rules. You could hurt people and stuff. I don't know why we did that. All right. Number 19 is potassium. So K, and there you go. All right. And there is such a thing as positron. So when we talk about it as alpha, beta, or gamma, it is called decay. With positron, it is called emission. So emission means to lose. I don't know why they don't call it decay. That would be a historical fact. So sodium is 22 and 11. So again, they all have something unstable. Sodium, probably closer to its mass of 23, is the stable. The numbers on the periodic table are usually around the stable one. So this must be something when sodium is at 22, for some reason it's not stable. And so arrow, it's going to go to a positron. Again, you can show it as a little e or the beta with a +1. And mass, again, does not change. Electrons, beta particles, positrons, gamma. And this is a +1 on the product side. So it did drop to number 10, which is neon, which is probably also not stable. All right. Filling in the blanks here, oxygen, just fill in your lower numbers. Oxygen's number 8, nitrogen's number 7. So the mass, we need a 1 to make the 15 and 14 balance, and the 8 and 7, we need a 1 here. So if you have a 1 and a 1, there's two ways you could write it. You could say, well, that's hydrogen, right? Because hydrogen's number 1, or it's a proton. Either way. Sometimes I have where you circle an answer, and so it might have it as words like positron, proton, neutron. And so realize this is the alternate symbol for a proton. It is not, when we're talking about all of these, we're ignoring all the quantum stuff on the outside. This is all about the nucleus. All right, nitrogen is 7, carbon is 6. So we need a 1 again, but the mass did not change. So this is, you can write it like that, or it's a positron. Right, and then strontium 38, it is, again, what's used by helicopters to keep the timing right. This radioactive strontium, and deuterium's right next to it. And so some of you become really good at this, and you can say, oh, well, if it moved this way, it must be beta. But you can always check. The mass did not change. This would have to be -1, so that the side of the arrow is going to give us a 38, which is our number there. So we can write it like that, or beta decay. And all right. This one, just be careful how it's worded. The arsenic is formed. That's telling you the arsenic is the product. So arsenic is number 33. The beta particle is over here with it. So again, it doesn't matter what order you write it in, just that these are both on the product side. And so we would have started at 32 and 77. So 32 is germanium. Yes. So again, formed means it's the product, or the daughter is historically what they would call it. So, sorry. I know it shows up. It probably shows up on the study set for Tuesday. Again, most of them go through several steps. So you'll see one that will say it goes through this step, that it will go through alpha, alpha, beta, beta. You can write every step, but there's a way to figure out. So you can try it, or you can leave that one blank when you get on the homework. Show up on this. We're going to move on just for time. So this one is a prediction. That's all it can ever be, is a prediction. You have to actually, they have to actually do the decay, and then they can measure what type of particle it is that comes off. So there is something known as the band of stability, and it is a ratio of the neutrons. So these words are really small, but that is neutrons and this is protons. And this picture, this graph looks like it's from the 40s because it is from the 40s. And this line would be if it was a 1-to-1 ratio, that's what that says. 1 proton to 1 neutron. So this chart is actually here on your periodic table. If you look at the smaller elements, their mass number is usually closest to the most stable isotope. And the mass number is usually, or the atomic mass is usually about double the atomic number. So 5 to 10, 6 to 12, 7, 14. So it's a 1-to-1 ratio. But as we go on the periodic table, it's much more than double. Like if you look at xenon, we would want this to be a 108 and it's 131. And so what's having to happen is you need, it's not a 1-to-1 ratio. The band starts out 1-to-1 and then it curves up. You need a lot more neutrons to stabilize because protons are positive. And so those protons are all being held in that, what we consider, right, that really small space. All the mass is in there and all this positive, and the positives should not want to be near each other. And so you're needing more and more neutrons. And so you're gaining more neutrons for every proton. If you're above the band, so if you're up here, you have too many neutrons. So if we go back to our notes, a neutron can be changed into a proton. That's going to be beta decay because it's a neutron changing into a proton plus a beta. We did that on the first page. And so that's going to lower it closer to, this is where they're stable. So here they're stable. They don't decay. If you're below the band, you have too many protons. And so that's going to tend to go through positron emission. Because again, that's a proton becoming a neutron plus a positron. I know I'm going fast, but you can go back and look at it. Most students do really great with this. You just have to put a little bit of time in next Tuesday and do your study set before class. All right, once they get really big, they're just too big. Kind of like they're an American and they just have to lose weight. So they're going to go through alpha decay. That's not 100% true. We saw on the previous page, uranium-235 goes through beta. All the other forms of uranium go through alpha, but 235 goes through beta. So once they get too big, they're always unstable. Everything past bismuth is unstable. There's no stable form of it. There's just too many protons. Now, something else, oh, must be on the next page. We'll come to that. It's on a later page. All right, artificial. So these are predictions. Basically, you look at the periodic table. So for the prediction, look at the mass number on the periodic table. The mass number on the periodic table tells you this band. So if you had something, let's say like boron 12, I have no idea, I'm just making up a number. So if I gave you boron 12 and said what's going to happen, you would say, well, that's too big, it has too many neutrons because it's higher, it's going to be above the band, so it goes through beta. If I gave you boron 8, you would say, oh, that's too small, it's lower than the normal, So you're looking at, I'm sorry, the mass, the atomic mass, the mass. Yeah. All right. So you can try it. There'll be one question on the study set, and so we'll see that. Artificial transmutation means man-made. So alpha, beta, that's natural. It's what it does. This, anything's possible. This is where they put in the cyclotrons. This is what CERN, the labs are. So the cyclotron was what was made by Lawrence. He got his name on the periodic table. Seaborg is the guy who worked on that. And there's actually, again, you can pick your topic. There's a lot of cool stuff out of CERN. And they have an amazing website that is like really simplified for brains like mine. And so this is, again, not spontaneous. It's a man-made process. So that would be a fun topic if you want to do something like that. All right. You can even do a fictional one. You can go into the Marvel comics because they do actually some fun ones. I had somebody do that one year. Because what is Captain America's shield is made out of something. Anyway. There's actually a lot of information on the web because it's like a whole cult thing. So the thing where it's man-made is we're going to have two reactants. So they're colliding. They're causing a collision to happen with magnets, like high speed. High speed is like, we can't even imagine this. That's where they're using the magnets. And so you just fill in the numbers. So we have a 7 and a 2. We add them together. So we have to have 9 on both sides. So oxygen is 8. This would have to be a 1. My numbers on top, 14 plus 4 will give me an 18. So I have to add these up. So I'll have a 1 and a 1. So again, you can write it as hydrogen or proton. Either way is fine. All right, next one. Aluminum is number 13, and this is a neutron. So if it's little n, that's a neutron. So we have to get to 13. Then we have 27 plus 1, so we have to get to 28 on the upper numbers. So we get sodium 24, which is definitely not stable. It's nowhere near that number on the periodic table for, well, it's not nowhere near, but difference from 23 to 24. So they don't make things that are stable. They're just making new isotopes to see what they can do with it. This would have to be a 4 and a 2, which you can write as helium, or 4 and 2 is
Alpha.
alpha. Here we go. Captain got it. Captain Max, finally. So you can write it either way. You can show it as a helium or an alpha. That doesn't matter because this is, again, not decay. And then this one, we put our 8 and our 1. Here's our arrow. So the two sides, the numbers have to be equal. So we have to get to a 9. This looks like an alpha again. So we get a 2 and a 4. So again, you can write as helium or alpha. A quick comment for you. You're not going to get multiple different things. There's one thing on the arrow. So don't make it like 4 different particles, a proton plus a neutron plus a neutron. It comes off as one package. All right. Uranium-238. And it captures. So again, capturing means they're throwing a neutron at it. And it captures it, and it becomes bigger. So it becomes uranium-239. And that's what they did for a whole bunch of stuff. They could make them bigger and see what they would get. The thing was, when they did it with uranium-235, they got small pieces. They didn't go bigger, they got smaller. And this is fission. So fission is splitting the nucleus. And it took them a long time to figure out what they were doing. Liza Meitner is the one who figured it out. She was Jewish in Germany at a time when it wasn't safe. And so she left everything, her lab notebooks, everything, got on a train and left. Otto Hahn, there's two Ottos, and one of them's her cousin. And so there's like this whole controversy because Otto got a Nobel Prize for her work. She didn't care. She just did the work because she wanted to understand and make everything understand. So there's all this stuff where we go into, oh my God, these people got ripped off. They weren't that worried about it because they were too busy in the lab working. That's all they cared about. They didn't care about prizes. I know that's hard to believe. All right. Anyway, so the story is, this could be a myth, but it's a really cool story that so they kept getting smaller pieces. They couldn't figure out why they kept getting smaller pieces. They would do it again. And then the story is that it was wintertime. There was snow on the ground. They were out for a walk, the two of them. And Otto's shoe was untied. He bent down to tie it. And Liza kept walking and talking. And then Otto stood up and threw a snowball at her. And of course, when he hit somebody with the snowball splits. And Liza didn't get upset. She said, what if we did that to the uranium? I don't know if that's a true story or not, but it's a wonderful myth. And it was a huge step because you have to realize they're seeing something smaller, and we see the picture after and we're like, of course they're splitting it, but they just kept looking at it going, because the thought of splitting the nucleus was thought to be impossible. And so the concept wasn't there. And so for somebody like the Nucleus, when he kept sending them in there and 99.9999999% went through, it took him a year and a half to finally say this has to be what it is, and to say all the mass is concentrated. One of the things I wanted to mention also, the nucleus is not a mayhem of stuff concentrated in there. Everything is organized. You're just at such a small level. And so they are organized, the protons and neutrons, in little rings, just like around Saturn. CERN has a really cool information on that. We get to that in a couple pages. We'll look at it briefly. So fission is splitting the nucleus. Into smaller pieces using a neutron. It is unpredictable what you will get, other than you will get something smaller. So I'm not going to remember the number right now. I used to know it. I think there's like over 300 different ways you can split uranium-235. So you always get two. This is a beautiful picture. There's a neutron. It always splits into two smaller pieces. They're not the same. They just have to add up to the total. And you always get neutrons. So uranium-235 undergoes fission, means plus the neutron. So that's the key. Plus the neutron is what fission is. And then you will be told what you make. So barium-141, again, I think there's over 300 different possibilities. 92 Kr, and we can add up the numbers. Krypton is 36. Barium is 56. And now we add up. So I gave myself more room on this page. 235 plus 1 is 236. 92 plus 0 is 92. So the two sides of the arrows, the numbers have to equal. So the lower numbers do add up to 92. So we've accounted for all the protons. When you add up the upper numbers, you only get 233. So what you got was 3 neutrons. So this is called a chain reaction. You just need 1 neutron to start it. You always get more out. Those 3 neutrons go and react with 3 more atoms. We're dealing with 1 atom at a time, and they give more. And so this is all happening in a femtosecond each reaction. So in under a nanosecond, you've got, this is out of control. So this is Liza Meitner, who has, I think it's called an epitaph. Her tombstone, you should Google it. What's written on her tombstone is pretty amazing. And there's Otto. This must be when she was still in Germany. This is Enrico Fermi, who did the first controlled nuclear reaction. He came up with the idea, the formulas and stuff. So he won a Nobel Prize. He lived in Italy, which was Mussolini. So when he went to Stockholm to get his Nobel Prize, he got on the wrong plane. Not only did he get on the wrong plane, he ended up in the luggage compartment of a plane that ended up in the United States. So we basically smuggled him out of Italy. He ran the Manhattan Project. He did, this is a great story, the first nuclear reactor was built in a racquetball court on the campus for University of Chicago. University of Chicago is smack in the middle of Chicago. So if you think the Transformers did damage to Chicago, this could have done a lot more. And so he went to the president of the university and said, I want to do this. And the president looked at him and said, if you ask me, I will say no. So basically, if you've never heard that answer, it means please don't ask, just go and do it and don't tell me what you're doing. So what the control rod was, because you're getting all these neutrons off. So what's happening in a nuclear reactor is they have control rods that are absorbing some of the neutrons to keep it from going critical, which is the point where it's exploding because so much energy is given off in such a small time. So the control rods used to be graphite. Now they're different elements. And some of you actually mentioned that when you did your element papers, you talked about, oh, it's used as a control rod. And so I think it was graphite then, I can't remember, but what the control was in case it didn't stay controlled was a graduate student sitting up on the beam above the racquetball court with an axe to hit the thing to fall down into the reactor. And I'm like sitting there going, but it would have gone critical before a human could have the reaction time to hit the axe. So thankfully they controlled it, and then the Manhattan Project grew from that, for better or worse. But right, so we entered the atomic age. So this is the atomic age, which we're now in the information age, studying quantum mechanics. So the amount of energy released is, there's no comparison. So I don't think it's on your study site. I think it's on the last lab. I moved the question. There is a math question you're going to do and calculate if you have like just 1 gram of uranium, how many tons of coal it is equivalent to the amount. This is 10 to the 10th. Like when we're doing our chemical reactions, like for octane and stuff for your car, we're getting 1,000. Like from a certain amount, several gallons of octane, we would get 1,000 kilojoules per mole. This is 10 to the 10th. This is 10 million times more. There's no comparison. The amount of potential energy that is stored inside an atom is something that we can't even conceive of. So the idea of the critical mass, this is beyond my understanding, but most uranium, 99.9% of uranium, the reaction here, most uranium is uranium-238. It just absorbs the neutron. And so the reaction can't happen. And so they had to isolate the uranium. They had to separate them. And they only have to get to a small percentage of uranium-235 in the sample for it to get to the point where they can run the fission. And so that was the thing that happened in Tennessee. They were figuring out a way to get a higher concentration of uranium-235. Hanford, they were trying to make plutonium, because that's a question in the study set, that if you take uranium, it will actually, the next step here is it goes through 2 decay steps, 2 beta decays, and you end up at plutonium-239. Very few things go through fission. That's actually a good thing. Your uranium-235 goes through fission, and plutonium-239. And so we were able to make very pure plutonium-239 because most of uranium is uranium-238. So again, this reaction, you go through 2 betas and you end up, oops, with plutonium-239, and that can go through fission. That's what they did at Hanford. And then down in New Mexico is where they tested the first atomic bomb. You can't get anywhere near the Trinity site. You wouldn't want to, but it's still pretty cool history. All right. Fusion is the opposite. So fission is splitting. Fusion is taking 2 or more small nuclei and fusing. And you fuse. You bring them together. And that is what happens in all the stars. That is the energy of the stars. This is the conceptual idea of what a fusion reactor would be. You have to have extraordinarily high temperatures, like the sun. You have to contain the plasma, which they have been able to do. So once you start doing this, the nucleus and the electrons are not bound together anymore. And so it's behaving totally different from how you and I behave. They just haven't been able to tap into it yet to recover the energy. The bad news up here is you get waste. These are radioactive. It's not a huge amount of waste. So submarines are nuclear subs. They're using nuclear energy. The amount of waste that they generate from like a 3-month is like enough to fit into like a test tube or something. I don't remember what the number is. I had a student one year who had for 4 years in the Navy been on a nuclear sub. So they get to learn about all this stuff. So that's where the controversy. The other half of the controversy is if humans can be trusted, and that's a whole different question. So fusion is that they have done fusion. They've been doing it for a while. We just haven't been able to tap into it. And so who knows? The first nuclear reactor is in Idaho. You can go see it. It's in the middle of nowhere. And it was Eisenhower. So after the war, nuclear got a really bad name because of when we dropped the 2 bombs on Hiroshima and Nagasaki, and like people suddenly went, whoa, what just happened? And there's a lot of really cool stories though about some of the stuff that happened. So they were trying to promote, that's where nuclear treatment for cancers came from, because they were trying to make people pro-nuclear again. But anyway, the first nuclear reactor, middle of nowhere in Idaho, it's worth seeing. It closes at 5. You show up at 4:59, they're not going to let you in. Yeah, and that's because it's in the middle of nowhere. Nobody lives there. So people are busted. There's also some kind of weapons stuff going on there. In that part, I don't know anything about. Utah has some interesting stuff too. All right, because they're all in the middle of nowhere. So units, all you need to know about units is they're different, and they're going to be a symbol. So a curium, Roentgen, he was the guy, first Nobel Prize for X-rays. A rad is radiation dose, and a rem is how much damage to us. Right. And so we're always exposed to some. Biological effects, you guys all know them. But there's more to all that, because you're also dealing with, we're vibrational beings, and so can have an effect. So you can look at my friend Bruce Banner, right? He had the gamma ray. The organs that are going to be affected the most are like reproductive, because then offspring. But it also, for women, like the uterus has any organ where it has a fast cell turnover time is the most susceptible. And so for women like Chernobyl and in Hiroshima, it was like uterine cancers, and those cancers just skyrocketed, the ones who didn't die. Thyroid is really susceptible. If you know anybody who's gone through like different types of therapies, I don't know why bone marrow is another one that's really susceptible. All right. Half-life we've talked about. So just a reminder, it is a natural log. So natural log of 1/2 equals negative KT 1/2. It is always first order decay for radioactive. And so we can, you guys know how to do this. So this is, again, the initial. So the idea, this is carbon dating, is we all are carbon based. And so we're always taking in carbon, right? We're eating. Everything we eat is carbon based. And there is always some radioactive carbon. Carbon 14 is unstable. So carbon 14 is unstable. It has a decay time of every 5,700 years, half of it decays. So in our body right now, if you took a sample of our bones, there is a ratio of carbon 14 to carbon 12. Once you die, in case you didn't know, you stop taking food in. So you're not taking carbon in anymore. So the carbon 14, every 5,730 years, there's less of it. Carbon 12, so the ratio changes. And so that's what they're looking at. And so this only works if the artifact that they're looking at has carbon in it. There's other dating ones that they use for other things. So argon is actually really fascinating. They do dating with different stuff, and they're all an approximate. It's like we can get roughly how old things are. But that's what this is. These units don't matter because remember, it's going to be that ratio of AT over AO equals negative KT. So this is telling us this is the initial, this is the final. You would use the half-life to solve for K. And so this is just like what we just did. I'm going to move on just because you would first find K using the half-life formula, right? And then you would do this to figure out your time. And it makes sense because it has not gone through a half-life yet. So 19.5, we haven't ended up with half of it. So it should be less than a half-life. So it's less than one half-life. On the next one here, it gives us the half-life is 110. It wants to know what percent after, so 5 hours is about 300 minutes. So you could go through all of it. Now realize we've gone through 3 half-lives. So after you start at 100, you're going to end up at 50, 25. We should end up, you know, around 12.5%. But I'm telling you it's 84. And that is because of how the question is worded. And so when you solve for AT, you're going to actually get 15.1% or 0.15. Your ratio of AT to A0 would be 0.15. That is how much is left. So how much remains? So always be careful how the question is worded. So on the worksheet, I think I worded it different for different questions. So this is how much remains. This question wants to know how much decayed or disappeared or decomposed, which would be 100 minus that. So about 85% is gone. And that makes sense because it's roughly 3 half-lives. So we're roughly around 12%. Again, we can only say roughly when we're doing a quick prediction. And again, I was just, anyway, you can stay after and ask if you have a question, or we'll see that. We did that with kinetics. So we'll move on to the really cool page. This, and again, you're going to, for the last lab, and I will open the folder, or somebody can remind me if I forget to. if you want, you can look into this. And the CERN website had, I just remember several years ago, I went on and they had like a really cool video. It's made for kids, so I could understand it. So this was Seaborg's idea, which is why I wore his shirt today. Somebody gave me this shirt. So Glenn Seaborg, whose picture is over here, he is the guy who ran all these experiments that made all these elements down here. And he had this idea, not the band of stability, but there are certain elements that certain isotopes are extremely stable. I don't remember them. There is, I think it is tin 120 is one of them. I know tin and calcium were two of them. There's 4 elements, and there's a mathematical way, and their prediction is, and I can't remember now, it's going to be element number 126, but it's a ratio of protons to neutrons. So they've made element 126. It's not on my periodic table. I don't think it's on any of our periodic tables. They haven't had the neutrons right yet, but the theory is that when they can get the right number of neutrons with this many protons, that element's going to be stable. And anyway, it's a pretty cool idea. Glenn Seaborg came up with this idea, and apparently there's been enough stuff. His element was controversial for the first 10 years that I was teaching because he was still alive. And so they say you cannot have your name on the periodic table until you're dead, which is a stupid rule. And so there were like 2 different periodic tables out there, some that had his name and some that said you can't have his name on there yet because he was still alive. But he lived a long time also. But he had having purpose in life, and he had great purpose. Yeah, so all the elements past 101 are very unstable, but he had this idea. There's certain isotopes of certain elements, and there's a magic number. And I can't find my notes where I wrote this down, but you can Google it. And again, in that last lab, you could do one more of those 1-page things. And if you want to look up the magic numbers for stability. So what we're going to do, the last thing, is we're going to calculate binding energy. And this is the energy, this is your teacher's really simplistic way of understanding it, but it's basically the energy to hold the nucleus together. Or the energy stored in the nucleus, maybe we should say that, the energy stored in the nucleus. So the protons and neutrons, so this is the part that's fascinating. So there are 4 forces, right? There's gravity, there's the positive, negative, electrostatic, and then the other 2 forces are actually totally made up. They're the strong and weak nuclear force, and they made them up because it's the only way any of the math works out. So that's where forces come from. Somebody's like, well, we have to have it. There's apparently some more out there. We just haven't found them yet because they're quantum forces, and that would be dealing with how electrons behave. And we have yet to fully understand what that is. All right, so these are the masses of protons and neutrons to more sig figs. There's a guy who's going to win the Nobel Prize soon who's really young, who said the mass of the proton was calculated wrong, and he had a theoretical way. It turned out he was right. He's a really interesting guy, and he actually is very much into meditation and all this esoteric stuff. And he gives talks at yoga conventions as much as he gives talks at physics conventions. Because if you're working in quantum mechanics, you can only be working in that if you're ready to go into the woo-woo area. All right, because it's all the same. So the mass defect is that if you add up the mass of the protons plus the neutrons, it is not equal to the mass of the atom. There's always a difference, and that's called the mass defect. And where this is going is E equals mc squared. that mass defect, the difference between these, if you multiply that number by the speed of light, and this is what Einstein's equation, and so this is like the coolest problem we ever get to do, because we're going to get to use Einstein's equation. So when we get done with this in a couple minutes, you'll get to tell people, I used E equals mc squared tonight. So the binding energy, if we add up, so it's nitrogen 14. There are 7 protons plus 7 neutrons. So we would take the 7 protons times this number plus the 7 neutrons times that number. And I already did the math. All right. Was that 1.00867? And then, so those two minus nitrogen 14, which I gave you the math there. So we would, and the units here are AMUs, which is just that funky U for right now. We'll change the unit in a moment. So minus the 14.00307 AMUs. So you'd punch that in your calculator and you get that the change in mass doesn't equal that you end up with 0.11243. Now realize I've had students say, well, the difference is because we're not factoring in the electrons. An electron is 1/1820th of an AMU. We'd have to have like a couple hundred electrons, and nitrogen only has 7, so it never adds up to the total. There's always a difference, and so that's where this theory comes from. The other piece is in the calculation. So this is the unit for AMUs is grams per mole. So we're going to change this to grams per mole. For this to work in E equals mc squared, E has to be joules, and a joule is a kilogram meter squared per second squared. So if we take the 0.11243 grams per mole, we have to change it to a kilogram to be able to make it a joule. So 1,000 grams to 1 kilogram. And then just remember the speed of light, 2.998 e to the 8th meters per second, and you square it. So that's C. Remember that from when we did quantum mechanics stuff? And I take it one more step, because if you remember, your teacher always says kilojoules. So this is joules. So 1,000, so 10 to the third joules to 1 kilojoule. Sorry, our dinosaur is getting destroyed there. So what we find is our change in energy is 1.011 e to the 10th kilojoules per mole. And the reason my answer is a different answer is because I wanted it per mole of nucleon. So we'll take it one more step, which is for every 1 mole of nitrogen, 14, there are 14 nucleons. So I divided by the 14 nucleons, and that's where I got my answer up there. But that's the idea, that the difference, when you add up the parts, it never equals the whole. And so mass is just energy that has accumulated. It's energy with a lot of potential. That's what quantum mechanics is. It's energy with potential, and it starts attracting matter. And that's the thing that's really interesting. because we're on the verge of really truly understanding it. I mean, that was the whole idea. Jesus figured it out. So he went off and fasted for 40 days, and I don't know. I think I'd probably die. I don't know. But a lot of these guys have been quantum masters, and they've walked around, and that's what they're able to do. Except we're like, don't want to give it up. And so we've become accumulators. And so if you look at like what happened during coronavirus, people accumulated even more stuff. Like how many packages are in people's front porch from Amazon every day, right? The FedEx truck is like, you used to never, a year ago, you wouldn't see the FedEx truck. You'd see it like once a week, and now it's like 5 times a day it's on your street. It's like 5 times an hour. And the Amazon planes flying over. All right, I'm on his tantrum again. Stop recording.